Today's lecture will be divided into two parts. The first one is the recap about what you have learned regarding the multi-layer perceptron derivation. And then second part, I will show you in terms of how you can construct your model under Python environment and how you can do the design for the simple neural network model which consists of the multiple layer. So first thing first, in terms of the derivation part, for the derivation, if you still remember, the derivation will be constituted of the two parts. The first one is the chain rule. You derive the chain rule based on the given model. So this is the chain rule. And then secondly, when you have construct the chain rule, you will calculate the forward propagation and back propagation based on the chain rule. So most of the times the back propagation will directly relies on the chain rule that you have developed. So for the chain rule will be maintained for every three-layer model. So in our case is the three-layer model. Three-layer models means that you have input layer. This is the one. You have input layer, you have hidden layer, and you have output layer. So this is the three-layer models. So for this case, the chain rule will be retained for every configuration that you have changed, that you want to change, either the activation, the bias on everything. So basically for the chain rule, we can divide that thing into two parts. The first one is the derivation from error to the WJK. Secondly is the derivation from error to Wij. So for the first part, which is dE over dWJK, you will have three chain rule. For this case, you have three chain rule. And then for the second part, which is from hidden layer to the input layer, you will have four chain rule. So three chain rule, four chain rule. So it's quite straightforward. So most of the subpart in the chain rule, you can find the solution directly from the forward propagation. So let's just quickly recap about the models and then how we derive the function for each part previously. So basically you have the three chain rule and then you have series of the you have the three layers model and you have series of the chain rule. So the first part is to derive the forward propagation, which is straightforward from input to the output. So once you have that series of equations, so the next part is to calculate what is the delta WJK and delta Wij. So we have found that this is the equation for delta WJK, and all this equation will be directly related to the chain rule that we have derived from this part, in which for delta WJK you have three chain rule. So this is the whole equation, means that dE over dOK, the output of the chain rule will be negative dk minus ok. dok over dnet k, the output will be 1 minus ok times ok. And then dnet k over dwjk, the output will be oj. So the same thing for the delta wij, in which you have four chain rule. So since you have four chain rule, so the first part dE over dnet k is a series of equation that you take from delta WJK without the OJ, and then the second part dnet K dOJ WJK dOJ dnet J OJ 1 minus OJ, and dnet J over dWij is the OI. So this is what we have learned previously. I have shown you how we are able to do the derivation and some calculation when you put some value. So last 2 weeks I give you some question in which our model originally is linear sigmoid, and then we change the model to linear sigmoid linear, in which input will be the same, hidden will be the same, but the output is linear. So the question is, what is your new function of forward propagation and back propagation? So basically for the forward propagation, so since linear, sigmoid linear, only the output neuron, we change the output neuron activation function. So basically OI will be the same, NetJ will be the same, OJ will be the same since we still use sigmoid, NetK will be the same. So only this part will be different since this part is actually our linear activation. So your OK is supposed to be OK equal to net K. So this part was changed. So the second part is for the back propagation. So as I've mentioned, your chain rule will be the same for the 3-layer configuration. So basically DE over DOK, since you not change anything regarding the cost function, so you will use the same function. So the next part DOK over D net K. So for this case, OK equal to net K. So DOK over D net K, OK equal to net K, DOK over D net K will be equal to 1. So you just need to change the value of the DOK D not K. So previously is OK 1 minus OK 1 minus OK. So since you change to linear, so this one just value of 1. And then finally d net k over dwjk, since you don't change anything regarding this neuron, so it will be maintained. So only this part will be changed regarding the output equation of the back propagation. So the same thing with the delta wij. Delta wij, since this part was changed, so we just pick up this thing, the value negative tk minus ok times 1 without oj. So then the rest of the part will be the same. So this is basically what will happen if you just change some minor part of the activation function. So question number 2, if the activation function is changed to linear, sigmoid, tangential, so it will be almost the same, only these times your output not activation function, the activation function was changed to the tangential activation function. So the same thing will happening for this part, which is OI will be the same, net J the same, OJ the same, net K the same, only the output part in which we will use the tangent sigmoid activation function, which is E net K minus E minus net K over E net K plus E minus net K is the exponential parameters. So for the forward propagation, OK will have a different value, and then for the back propagation, so the same thing, this is will be the same, and then this will be the same. So the one that will be changed is dok over d net k. So since OK equal to e net k minus e minus net k over e net k plus e minus net k, so we just differentiate this equation dok over d net k. So eventually you will get 1 minus OK squared. So we just need to plug in back the value here. So you have the full derivation of the delta wjk, and the same thing happening for the delta wij, since you pick up the value that you obtained here and then just put it in this part. So you have the whole equation when you change the output activation function to the tangent sigmoid. So I left you with the derivation, how you were able to derive the OK in order to obtain the dok over d net k. So the answer will be 1 minus OK squared. So please try to derive this part until you get this equation. So the final part is if the model is as follow, what is the expected forward propagation and back propagation? So in this case, we have the same model, linear sigmoid. Only the thing that is different from our first model, which is here, is that for this final part, you don't have any bias. You don't have any bias connected to the hidden layer and the output layer. So for the FP and BP, basically majority of the equation will be the same. So for the forward propagation, it's almost the same, only without B, J, and BK. For the back propagation will be the same. So for the FP, what is the thing that will be different is this part. So for this case, we just need to construct the whole equation, only this time without BJ, without BK. So this is just the whole equation for the forward propagation. So for the back propagation, more or less it will be the same, and you don't have any equation of adaptation of weight for the bias in terms of the BJ and BK. So hopefully you understand better regarding the derivation process and how you can manipulate a bit in terms of the chain rule value. When you change the activation, you change the structure and etc. So that's all. Thank you very much for the first part.